All right, today we're going deep on an element that is just full of contradictions. I mean, it's the super soft graphite in your pencil, but it's also the hardest diamond on the entire planet. We are talking about carbon, and trust me, it is way more fascinating than you probably think. Let's get into it. So, let's start with a little riddle. What is the one thing that connects the hardest stuff we know of, a diamond, to the actual DNA that makes you, well, you? You guessed it, the answer is carbon. And how in the world it manages to pull off this incredible range? Well, that's the mystery we're going to solve today. Okay, here is our very first clue, and honestly, this is a bit of a shock. Get this. That number is how much carbon is in the Earth's crust. Just 0.02%. That is practically nothing. So the question is, how could an element that's this scarce be the backbone of, everything?
Well, if you thought that was strange, check this out. This number, millions, is roughly how many carbon compounds we know about. That's more than all the other elements put together. So what gives? We've got this huge paradox. How can the rarest ingredient be the star of the most recipes?
The answer to that puzzle starts at the absolute smallest scale you can imagine, the single carbon atom itself. And as we're about to see, the carbon atom has a really big problem it needs to solve.
So here's the quick file on carbon. It's atomic number 6. That means 6 protons in the middle, 6 electrons buzzing around it. But the number you really need to pay attention to is 4. Carbon has 4 electrons in its outermost shell. These are called its valence electrons, and they're the ones that do all the work in chemical reactions.
And those 4 electrons are the source of carbon's big dilemma. See, to be stable, an atom wants a full outer shell, which usually means 8 electrons. So carbon could try to grab 4 more, but its little nucleus with only 6 protons just isn't strong enough to hold on to 10 electrons. It becomes unstable. Okay, so option 2. It could just give up its 4 electrons, but that takes a massive, massive amount of energy. So it's stuck. It can't gain them, it can't lose them. So what's an atom to do?
This is where carbon gets clever, really clever. It finds this incredibly elegant way out of its jam. Instead of trying to steal or give away electrons, it comes up with a better idea. Why not share? And that simple idea, that one little shift in strategy, changes absolutely everything.
This sharing is what we call a covalent bond. It's not a power grab where one atom rips an electron from another. No, it's more like a friendly potluck where 2 atoms each put electrons into a shared pool. It's a brilliant workaround that lets both atoms feel like they have a full, stable outer shell.
And it's not just carbon that does this, by the way. You see it all over. 2 hydrogen atoms can share 1 pair of electrons, making a single bond. 2 oxygen atoms, they can share 2 pairs. That's a double bond. And 2 nitrogen atoms can even share 3 pairs, forming a super strong triple bond.
And that brings us right back to our hero, carbon. Look at this molecule, methane. You've got 1 carbon atom sharing its 4 outer electrons with 4 different hydrogen atoms, and it's a total win-win. The carbon atom gets to feel like it has 8 electrons, which is nice and stable, and each hydrogen gets the 2 it needs to be stable. It's a perfect deal. Everybody's happy.
But this is really just the beginning of the story. Because this simple trick, this ability to form 4 stable, shared bonds, it unlocks 2 incredible and unique abilities. Let's call them carbon superpowers. Okay, superpower number 1 is called catenation. Yeah, it's a fancy word, but the idea is simple. It just means carbon is exceptionally good at forming strong, stable bonds with other carbon atoms. This lets it build stuff, long chains, structures with branches, even complete rings.
And you can see it right here. You start with 1 carbon, that's methane. Then you link another one on, boom, you get ethane. Add a third, you get propane. Carbon can just keep on linking up, creating these amazingly long and stable backbone chains. And this ability to link up with itself, that's almost totally unique in the entire periodic table.
Superpower number 2 is tetravalency. Tetra just means 4, right? So this is simply carbon's ability to form 4 bonds at once. Now, when you combine this with its first superpower, catenation, well, that's where the real magic happens. It's not just building in lines anymore, it's building in 3D. This is such a great example. Okay, look at these 2 molecules. They have the exact same parts list, 4 carbons, 10 hydrogens. That's butane. But on the left, you see the carbons are all in a nice straight line. On the right, one of them has branched off. Same pieces, just assembled differently. And because of that, they actually have different properties. We call these structural isomers, and they exist entirely because of carbon's 2 awesome superpowers.
All right,
If you thought that was cool, hold on. Let's look at the most dramatic proof of carbon's versatility. We've seen how it can build different molecules, but what happens when it only bonds with itself? Well, you get what are called allotropes, wildly different physical forms of the exact same element.
So first up, we have diamond. In this arrangement, every single carbon atom is locked into place, bonded to 4 other carbons in this super rigid 3D lattice. Think of it like a perfect jungle gym, where every joint is welded solid. That interlocking structure is exactly what makes diamond the hardest natural substance we know.
Now, take those exact same carbon atoms and just rearrange them. In graphite, each carbon is bonded to 3 others, forming these flat hexagonal sheets. You can imagine them like stacks of paper that can just slide right over each other. And that's precisely why graphite is soft, slippery, and what makes your pencil work.
And it gets even weirder. You can get carbon atoms to arrange themselves into a sphere, like a tiny little soccer ball. This one here is called a buckyball, and it's part of a whole other family of carbon structures called fullerenes.
So let's just put them side by side, because this is just mind-blowing. Diamond, rigid 3D structure, the hardest stuff around. Graphite, flat layers, soft and slippery. Diamond won't conduct electricity at all, it's an insulator. Graphite is a pretty good conductor. And I have to say it again, these are both 100% pure carbon. The only thing that's different is the geometry. It's just incredible.
Okay, let's bring it all home. It's time to tie all these clues together. We started with a puzzle. How can such a rare element be so incredibly important? Well, I think now we have our answer.
It's because of its unique properties, that clever covalent bonding, the catenation superpower of linking with itself, and tetravalency, the ability to form 4 bonds. These things together allow carbon to be the ultimate Lego brick. It can form an almost endless variety of stable, complex molecules. And these molecules, they aren't just abstract ideas. They are the literal basis for the food we eat, the clothes we wear, our fuels, medicines, books, and yes, every single living thing on this planet.
This quote really says it all, doesn't it? The defining feature of carbon is its unbelievable ability to show up in millions of different forms, with properties that are just all over the map. It is the ultimate shapeshifter of the periodic table. So, from the humble pencil in your hand to the very DNA that makes you who you are, carbon is the quiet, unassuming hero of this story. It's nature's ultimate building block. And that leaves us with one last, pretty exciting question to chew on. With an element this ridiculously versatile, what are we going to build with it next?